two topics today. I want to show you more examples about L'Hopital's rule. Then we turn to study section 9, antiderivatives. Have a brief review first. Number one, in total, we have so many times of indeterminate limits. When we compute a limit with a direct substitution, plug in A in X, if we get one of these, then we cannot tell the limit. Direct substitution fails, and the limit is called a difficult limit. To find a difficult limit, we need to turn to some other method. One of those methods is L'Hopital's rule. Suppose we want to compute this limit and we use direct substitution. Plug in A in X, and suppose we get 0 over 0 or infinity over infinity. In the case, this limit is a difficult limit. To compute this difficult limit, L'Hopital's rule says that we can use this formula. The right side, the limit of the right side of the equation is a limit of a quotient of two derivatives. Pay attention. L'Hopital's rule can only handle the first two times of difficult limits. If a difficult limit is of the remaining times, then we cannot directly use L'Hopital's rule. In the case, we need to transform that difficult limit into a difficult limit of the first two times, then L'Hopital's rule. Now, topic 1, more examples about L'Hopital's rule. Example 1, find this limit. The first try is direct substitution. Plug in 0 in X, then I get this number. Cotangent of 0 from the graph of cotangent. When X approaches 0, cotangent approaches infinity. So cotangent of 0 is infinity. So we get 0 times infinity. We don't know what is that. So direct substitution to compute this limit fails. This is a difficult limit. The type is 0 times infinity. Now, I want to use L'Hopital's rule to compute this limit. Now I transform the limit into a type of either 0 over 0 or infinity over infinity. Recall that cotangent is cosine over sine. So I can write this function as this function. When X approaches 0, cosine of X approaches cosine of 0. Cosine of 0 is 1. So I can simplify this limit by replacing cosine of X by 1. So this limit is equal to this limit and this limit. Okay, now let me compute this limit. Plug in 0 in X, then I get 0 squared over sine of 0. It is 0 over 0. So this limit is a difficult limit. Indeterminate by direct substitution, difficult limit. But because this difficult limit is of type 0 over 0, I can apply L'Hopital's rule. So this limit by L'Hopital's rule, this limit is equal to limit of derivative on the top over derivative on the bottom. Then we get this limit. To find this limit, try direct substitution. Plug in 0 in x, then we get this number. Now this time, cosine of 0 is 1. So 0 over 1 is 0. So this limit is 0. From here, we know that as x approaches 0, x squared approaches 0. Cotangent approaches infinity. Then why their product is approaching 0? Because x squared approaches 0 faster than cotangent of x approaches infinity. Therefore, their product is approaching 0. Example 2. Find this limit where x approaches pi over 2 from the left side. By direct substitution, plug in pi over 2 in x, then the limit is this number. Now, what is secant of pi over 2 and what is tangent of pi over 2? The graph of tangent is here. When x approaches pi over 2 from the left side, we can see that tangent approaches positive infinity. So this number is positive infinity. Then how about secant pi over 2? From the graph of secant, x approaches pi over 2 from the left. Secant approaches positive infinity. So this number is positive infinity. So we get infinity minus infinity. This is a difficult limit. The type is infinity minus infinity. To use L'Hopital's rule to compute this limit, we need to transform the limit into type 0 over 0 or infinity over infinity. By trigonometry, we know that secant is 1 over cosine. Tangent is sine over cosine. These two terms, they have the same denominator, so we can combine these two terms together to get the function, to get this function. Okay, now if we plug in pi over 2 in x, then we can see that 1 minus sine pi over 2. 1 minus 1, so 0. Plug in pi over 2 in the x here, cosine of pi over 2 is 0. Then we get 0 over 0. So this is a difficult limit, but the type is 0 over 0. We can apply L'Hopital's rule to this limit. By L'Hopital's rule, take derivative on the numerator over derivative on the denominator. 1 minus sine derivative is 0 minus cosine. Cosine derivative is negative sign. Okay, now plug in pi over 2 in x, then we get this number. Calculator. Cosine of pi over 2 is 0. Sine pi over 2 is 1. Therefore, we get 0 minus 0 over negative 1. The limit is 0. So this limit is 0. From here, x approaches pi over 2 from the left side. Secant approaches positive infinity. Tangent approaches positive infinity. But But the difference is approaching zero. That means that these two guys, they go to positive infinity at about the same speed. So the difference approaches zero. The limit is zero. Now, example number 3. Find this limit as x approaches zero from the right side. From the right side, that means that x is positive. X approaches zero, but x is kept positive. Now, direct substitution, plugging zero in x, then we get this number. What is lateral log of zero? Here is the graph of lateral log. X approaches zero from the right side. The curve goes down to negative infinity. So we conclude that lateral log of zero is negative infinity. The limit is 0 times negative infinity. We don't know what is that. This is a indeterminate limit. The type is 0 times infinity. To use L'Hopital's rule to find this limit, we need to transform the limit into either 0 over 0 or infinity over infinity. Now, let me transform the limit. X times lateral log of x. Let me move x to the denominator to get this. Now, as x approaches 0, lateral log approaches negative infinity. 1 over x will approach infinity. So this is a difficult limit. The type is infinity over infinity. We can apply L'Hopital's rule to this limit. By L'Hopital's rule, this limit is equal to derivative on the numerator lateral log over derivative on the denominator 1 over x. This is a L'Hopital's rule. Now, lateral log derivative is 1 over x. 1 over x, how to compare derivative of 1 over x? We can use quotient rule, but I want to use power, the formula for power function. I write 1 over x as x to negative 1. So by power formula, derivative on this guy is power negative 1 times x. The power is power minus 1, a minus 1, so negative 2. Negative 2. Okay, now simplify this function. X to negative 2. I can move it to the numerator to get a negative x squared. Cancel 1x, then I get this limit. Now, direct substitution. Plug 0 in x, then we get the limit is 0. So this limit is 0. When x approaches 0, x approaches 0. Lateral log approaches negative infinity, but their product approaches 0. Why? It is because x approaches 0 faster than natural log approaches negative infinity. So their product approaches 0. This limit is 0. Example 4. Evaluate the limit where x approaches 0 from the right. By direct substitution, plug 0 in x, then we get the limit is 0 to 0. 0 to 0 is indeterminate. So this limit is a difficult limit. To find the limit, we transform the limit into a form that we can tell the limit. We transform the limit by natural law. Okay, the power function, the tower function, this is a tower function. The tower function can be written into an exponential function by log. And recall that log reduces a power into a product. We can move down the power x in the front to get this. From previous example, when x approaches 0 from the right, x times natural log approaches 0. So when x approaches 0 from the right, the power approaches 0. So therefore, e to this power will approach e to 0. E to 0 is 1. So therefore, this limit is 1. Example number 5. Find this limit again, x approaches 0 from the right. By direct substitution, plug in 0 in x, then we get sine of 0 to tangent of 0. Sine of 0 is 0, tangent of 0 is 0. So we get this limit is 0 to 0. Again, it is indeterminate. Now we transform this limit into a form that we can tell the limit. From a trigonometry class, we know that tangent is sine over cosine. So this limit is equal to this limit. When x approaches 0, cosine of x approaches cosine of 0. Cosine of 0 is 1. So we can simplify this limit by replacing cosine of x by 1. So we get this limit. And then this limit. Okay, now here I make a change on variable. I let t below sine of x. Then this limit becomes t to t. T is sine, t to t. Okay. When x approaches 0, t approaches sine of 0. Sine of 0 is 0. So x approaches 0 is equivalent to t approaches 0. Okay, but this limit, we got this limit in example 4. In example 4, x approaches 0 from the right, x to x approaches 1. So this limit is 1. This limit is 1. Okay, so therefore, the original limit is equal to this, but this is equal to this limit. This limit is 1. Therefore, the original limit is 1. Topic number 2 today. This topic is about section 4.9, antiderivatives. 4.9 is a preparation section for chapter 5. In chapter 5, we will study integrals. Geometrically, a derivative is the slope of a tangent line. An integral, on the other hand, is the area of a region. Okay, then why do we need to study antiderivatives? It is because the computation of an integral needs an antiderivative. To compute an integral, we need to find one antiderivative of the function f. Say, let me denote that antiderivative by bf. Then integral is equal to bf evaluate at upon b minus the bf evaluate at upon a. For example, let's compute this integral. This integral is the area of the region between the x-axis and the graph, and also between 1 and 3. 1 and 3. 1 and 3. Yeah. So this integral is the area of this region. Then how to find the area of this region, or how to find this integral? Find one antiderivative of 1 over x. Say lateral log of x. Lateral log of x derivative is 1 over x. Evaluate lateral log at the number 3 minus lateral log at the number 1. Yeah, this number is the value of this integral, or the area of this region. Okay, here is the definition of antiderivative. Suppose we have two functions, little f and big F. If derivative of big F is equal to little f, then we say that big F is an antiderivative of little f. For example, sine derivative is cosine. So sine is an antiderivative of cosine. Similarly, sine plus 1 derivative is cosine. So sine plus 1 is an antiderivative of cosine. More general, sine plus c. C is an arbitrary number. Derivative on sine plus c is cosine. So sine plus c is an antiderivative of cosine. So cosine, this function, has infinitely many antiderivatives. However, cosine has only one derivative. Derivative of cosine is negative sign. So from this example, we see that a function can have many antiderivatives, but the function has only one derivative. Second example, this is the power formula for power function. Derivative on x to a is this function. So x to a is an antiderivative of this function. Example 3. It is easy to see that derivative of this polynomial is x squared plus 1. So this polynomial is an antiderivative of x squared plus 1. About antiderivative, one natural question is, given a function, how to find all the antiderivatives of the function? The answer turns out to be simple, just 2 steps. Step 1, find one particular antiderivative of the given function. Let me use this notation to denote that particular antiderivative. Here, P means particular. Okay, step 1, find one particular antiderivative of the given function. Now, step 2. All the antiderivatives of the given function are the particular antiderivative plus arbitrary number C. C is an arbitrary constant, arbitrary number. Yeah. So these are all the antiderivatives of a given function. Just 2 steps.